Welcome to Digital Logic Design course. This is going to be the second lecture of the course. Today we will talk about different number systems. The relevant sections are from chapter 1 are 1-3 and 1-4. In the previous lecture, we studied about analog and digital signals, different representations of digital signals, active high and low logic, and binary versus multi-level signaling. In today's lecture, we will study different number system, conversion of numbers from one number system to another, and how to perform various arithmetic operations in different number systems. We will start with the binary number system. In binary number system, the base is 2. There are two digits that are 0 and 1. Each one of them is called a binary digit or a bit in short. So a binary number is basically a string which contains a series of ones and zeros, right? So n bit can store numbers from 0 to 2 raised power n minus 1. So let's say if we have got a 2-bit number, so it can store values up to 2 raised power n, right, minus 1, right? So if we have got a 2-bit numbers, it can store 0 0, it can store 0 1, it can store 1 0, and it can store 1 1. So what is 2n? This n means number of bits, right? So if it is a 2-bit number, so it would be 2 raised power 2, which would become 4. 4 minus 1 would be 3. So it can store 4 values, right, starting from 0, and it can go till 3, right? So the highest value that can be stored by this is actually 2 raised power n minus 1. It is something which you should remember, right? Similarly, in positional representation, each digit represents a power of 2, right? So we have got, let's say, the binary number 101 in the binary number system. So if we see, take a look at this, so this is also a power of 2, this is another power of 2, and this is another power of 2, right? So this is called the least significant bit, the one on the right? And the one on the left, this one is called the most significant bit, right? Why do we define the significance in this way? This one actually carries a weightage of 2 raised power 0, right? We are multiplying it by 2 raised power 0. This one carries a weightage of 2 raised power 1, and this one carries a weightage of 2 raised power 2. So the significance basically increases as we move from right to left, right? 2 raised power 0, 2 raised power 1, 2 raised power 2. So this one is called the least significant, and this one is the most significant, right? Similarly, if we have got this binary number 110.11, right? So we have got a fractional part as well. So we would write it like this, like 1 multiplied by 2 raised power 2 plus 1 multiplied by 2 raised power 1 plus 0 multiplied by 2 raised power 0 plus. Now once the fractional part starts, right? So what we would do is we would start dividing them by 2, or we would multiply them by negative powers of 2, right? So this is 1 multiplied by 2 raised power minus 1, or alternatively we can also say this is 1 divided by 2, right? Similarly plus, right, the next digit, that is 1, it is either multiplied by 2 raised power minus 2, or you can say it is divided by 2 raised power 2, right? So this is how the numbers are represented in binary number system. This slide shows power of 2. These are some of the powers of 2 which are most frequently used once we are dealing with computer systems. Whenever we talk about memories or storage or any computation involving binary numbers, so we need to use very frequently these powers of 2's, right? So you do not need to remember them, but once you start using them, ultimately you are going to remember them. An octal number system, the base is 8 and we have 8 numbers starting from 0 and it goes until 7. So the highest number is 7, which is less than the base. Similarly, the octal numbers, if we consider any octal numbers, it would be a string of digits, right? It would include all the numbers 0, 1, 2, 3, 4, 5, 6, 7, but it cannot include 8 and 9, right? Remember, the 8 is the base, right? So in positional representation, each digit represents a power of 8, right? So if we have got 1 to 27.4 in octal number system, so each digit, that is 1, 2, 7 and 4, that is a power of 8, right? This one is the integer part. 7 multiplied by 8 raised power 0, the 2 it is multiplied by 8 raised power 1, and 1 it is multiplied by 8 raised power 2, right? The rules remain the same irrespective of the system, right? If we are talking about the fractional part, right, so we would divide it by power of 8, or we would multiply it by negative power of 8, right? So this would be 4 into 8 raised power minus 1, right? So it would become half, so that would 0.5. This would become 7. This would be 2 into 8, 16, and this would be 64 into 1, that would be 64. Right, so if we add this up, it would convert into 87.5 in decimal number system, right? Now, one thing that might come to somebody's mind, that is, why are we studying even the octal and the hexadecimal number systems, right? We can understand why we are studying decimal number system, because they are used by humans. The binary number system, it is used by computers, but why octal and hexadecimal number? Right? So the reason is that these number systems are used to represent binary numbers or the binary quantities indirectly. So instead of dealing with long strings of zeros and ones, that might be the case, right? So what we can do is we can employ the octal and hexadecimal in order to represent those long strings of ones and zeros, right? So what happens in octal, that in octal digit, it is basically, it can be used to represent three bits in binary, right? Similarly, in hexadecimal, each hexadecimal digit can be used to store or it can be used to represent 4 bits in binary, right? So instead of dealing with this notation like 001, 010, 111, it is difficult to remember, right? We can alternatively represent this in this short form, right? So 1 is basically 001, it is an octal number. This 2 is 010, right? And this 7 is 111. Later on we would see how do we convert number from one form to another. So you would see how this number is basically equivalent to this, or this one is equivalent to the binary one. In hexadecimal number system, the base is 16. It means that we should be having 16 digits starting from 0 and going till 15, right? So the numbers 0 to 9, they are included as such, whereas the numbers greater than 9, that are 10, 11, 12, 13, 14 and 15, they are represented using the alphabets, right? So A means 10, right? B means 11, C is 12, D is 13, E is 14 and F is 15, right? So the base is 16, so the highest number would be 15, but we won't be using 15 and hexadecimal. 15 is something else, right? We would be using F, and once we want to say 15, right? So this is a sample hexadecimal number B65F, right? If we want to convert it into decimal number system, as we have studied earlier, that each number would be a power of 16, right? So this would be 16 raised power 0, this F. This would be 16 raised power 1. This would be 6 into 16 raised power 2, and this would be 6 into sorry, this would be b into 16 raised power 3, right? So we would start from this end and start multiplying by powers of 16 in increasing order, right? So if you take a look at this is 16 raised power 0 multiplied by 15, right? So f is 15, then 5 into 16 raised power 1, then 6 into 16 raised power 2, and 11 into 16 raised power 3. B is 11, right? So once you are dealing with these hexadecimal numbers or questions or any conversion involving hexadecimal, so what you can do is on some right hand side of the paper or anywhere you can write these mappings if you don't remember them, right? So this is A is 10, B is 11, C is 12, D is 13, and then this E is 14, and this F is 15, right? So you can use then the mapping to work with these numbers, right? The same reason why do we study hexadecimal? So the reason is the same as that was for the octal, that it is even more useful for representing binary quantities than octal, because a single digit in hexadecimal number system can be used to represent 4 bits in binary, right? So let's say if I talk about this 15, it is basically equivalent to all ones. 1 1 1 1 is F, right? Similarly, if I talk about this A, so this is 10, which basically is 1010, right? So we would see how do we convert numbers from one form to another, but you should remember that why do we study the octal and by octal and hexadecimal number system. Moreover, these notations are also used once such some information needs to be communicated to the user by the computer, right? So the memory locations, although their locations, they are represented in binaries like 1 0 1s, but nobody remembers those long strings of ones and zeros. So alternatively, what we do is we denote those memory locations in terms of hexadecimal numbers. The numbers and different number systems are shown in this table. For example, if we take a look at this number 10, so this 10 is basically in base 10 or the decimal. It is equivalent to 1010 in binary. It is equivalent to 12 in octal, right? And equivalent to A and 16, right? Okay, so now we will talk about conversion of numbers from one base to another or from one number system to another. So in order to convert a number from one number system to another, we need to convert its integer as well as its fractional part, right? So once we convert both of them, right, then we would join the integer and fractional part of the number using a decimal point or a radix point. In performing decimal to binary conversion, we need to convert both the integer and fractional parts of the number, right? So let's say we have a number 41.6 at 6875 in decimal, and we are asked to find out the equivalent number in binary, right? So as we studied earlier, this number consists of two parts, right? One is the integer part, the other one is the fractional part, right? So we would convert both of them separately, and then later on we can join them together in order to obtain this number, right? So for the integer part, what we are going to do is that while converting the integer part, we will carry out continuous divisions by 2 and note the remainders in each step, right? So this is 41, right? What we are going to do is we would write 41 as such, and we would keep on dividing it by 2. So two 20s are 40 and the remainder is 1. Two 10s are 20, remainder is 0. Two 5s are 10, remainder is 0. Two 2s are 4, remainder is 1. And two 1s are 2, right? And the remainder is 0. So we would keep on doing this division till the time the remainder in quotient are either 1 or 0. So the equivalent binary number would start from the bottom as the most significant bit, right? So we would start draw an arrow like this. This one is the most significant bit and this one is the least significant bit, right? So we would start writing them like 1, then the next one is 0, next is 1, right? 0, then again we have a 0 and 1, right? So this is our equivalent binary number, right? Do not make this mistake. Some people use the inverted arrow, right? And they get confused between the most significant bit and the least significant bit, right? So this one is the most significant bit, right? And it goes over here, right? This one is the least significant bit and it goes over here, right? So the easy way to deal with this is that we draw an arrow from this to this, right? So in this way you won't make any mistakes, right? Similarly, if we need to convert the fractional part, right, so we will multiply it by 2, right? We would use this continuous multiplication by 2. We would note the number that we obtain, right? And then we would subtract the integer part, which would be either 1 or 0, and repeat the rest of the repeat the process with the rest of the fractional part, right? So let's say the number that we were asked to convert is 0.6875, right? So we do not know this number as of now. So what we would do is we would take this number 0.6875 and multiply it by 2, right? So it would give us 1.3750, right? So we would note this number, that is 1, right? And this rest of the number, that is 0.3750, right? We would write it over here, right? Ignoring the integer part, that is 1, right? And we would again multiply it by a 2. It would give us 0.7500. So this number we would note it, right? And 0.7500, it would again be multiplied by a 2, right? So once it would give us 1.5000, right? So this number we would note it over here, and 0.500 multiply would be again multiplied by 2, and we would keep on doing this multiplication till the time this number becomes the fractional part becomes a 0, right? So it would give us 1.0, right? So this number would be written, right? Now the arrow which is used for the most significance and the least significant, that is opposite to that was used in the integer part, right? So let me change the color. So what this means is that the significance, it is going to start from here, right? This was the most significant, and this 0 is the next one in significance order. Then this is next in the significance, and this one is the least significant, right? So we would write it like 0.1011, right? So 0.1011, this is actually the binary equivalent of the fractional part, that is this, right? So finally what we would do is 41.6 this is equal to the sum of the integer part as well as the fractional part. So this gives us the equivalent number in binary, right? So sometimes we might face some issues once we are doing the convergence of the fractional part, right? So while we are converting the fractional part, we in the previous slide we said that the fraction, we should keep on doing the multiplication till the fractional part becomes a 0, right? But this might not be the case every time, right? So the number might keep on repeating, it might not become a 0. So this doesn't mean that we will keep on doing the multiplication forever, right? So let's say this is the number 0.65 and we are asked to convert, it is a decimal number and we are asked to convert it into binary, right? So 0.65, if we keep on multiplying it by 2, right? So it gives us 0.10, right? And then we have 1001, 1001, 1001, right? So this is a recurring number in this 4 digits 1001. It would keep on repeating, right? So the fractional part repeats every 4 steps, right? And it would keep on repeating forever, right? So what is the solution to this problem? So one technique is that 101 0 0 0. So whatever is repeating, if you draw a bar on the top of this, right, that is the same technique which is used to denote like this is something which is repeating, right? And usually in such questions, the number of bits to the right of the decimal point, they are usually specified, right? So if you are asked to convert this number to 5 decimal places, right? So this means 10100, right? So this would be your answer, right? If you are asked to convert it till 7 decimal places, right? So this 10100011, this would be your answer, right? So then in those cases, we try to truncate the number or the answer to the number of bits that are specified in the question. While doing the reverse conversion, that is from binary to decimal, we can follow a technique which is in which we would multiply each digit right by their respective power, and we would add them up, right? So let's consider an example. Let's say we have a number 101001.1011, right? So it is exactly the same number that we obtained once we were converting 41.6875 from decimal to binary. Now we would try to convert it back, right? So you can carry out the conversion separately, right? That is the integer part separately and the fractional part separately, right? Or you can carry them out in the same step. Like what you can do is you can write plus and it would be 1 by 2, right? So first let's go through the separate conversion and then we would see how we convert them in one step, right? So this is first you are going to write this number 1 multiplied by 2 raised power something, we do not know that as of now, plus 0 multiplied by 2 raised power something, right? Then it would be 1, right? 1 multiplied by let me write it like this is 1 raised power 1 into 2 raised power something plus 0 into 2 raised power something plus 1 into 2 raised power something plus again we have a 0 into 2 raised power something, again a 0, 0 plus 2 raised power something plus, sorry, this is a cross, plus 1 into 2 raised power something, right? So what now you can do is start powers of 0 from here, 0, 1, 2, 3, 4 and 5, right? So you would start with power of with twos with 0 from here, and you would keep on increasing as you move from right to left, right? So this is 2 raised power 5 is 32, right? Plus 0 into 2 raised power 4, even if you compute it, even if you don't compute, because it is ultimately going to be multiplied by 0, so this number would become a 0, plus 1 into 2 raised power 3 is 8, plus 0, right? Plus 0 and plus 1 into 2 raised power 0, that is 1, right? So this would become 32 plus 8, that would be 40, plus 1, 41, right? Once we are doing the conversion of the fractional part, right, what we do is 1 multiply by 2 raised power something plus 0 multiply by 2 raised power something plus 1 multiply by 2 raised power something plus 1 multiply by 2 raised power something, right? So we are going to multiply it by negative powers in increasing order from this left side, right? So this would be 2 raised power minus 1, this would be 2 raised power minus 2, this would be 2 raised power minus 3, this would be 2 raised power minus 4. So it would be 1 divided by 2, right? This would become a 0. This would be 1 divided by 8. 2 raised power 3 is equal to 8, and this is a negative part, so it would go to the denominator, and 1 divided by 8. This would be 1 divided by 16, right? So 1 by 2, 0.5. This would be 0. This 1 by 8 is 0.125, and 1 by 16 is 0.0625, right? So if we add them up, we get this 0.6875, right? So what I was saying earlier was that instead of converting them separately, you can continue this conversion over here as well, right? You can say like these are the positive parts, and once you start with the integer fractional part, so you can multiply the numbers of the fractional part in with the negative parts of 2. Okay, so the process remains the same once you are going to convert a decimal number to octal, right? So previously, once you were doing a binary conversion, we were using 2 as the base, right? Once you are going to convert it into octal, so we would be dividing the number by 8, right? Because the base is 8 for which it is to be. Rest of the rules, they remain the same, right? So from here, this is you are going to use this repeated divisions, right? In the you are going to note the remainders, and you will keep on doing it till the numbers and the quotient and the remainder, they are less than 8, right? So this is how the decimal to octal conversion is actually carried out. That was the previous slide. It was for the integer part, right? For the fractional part, we would use the same rule that we used for binary. We would continuously multiply it by 8, right? So this is 0.513. So multiply it by 8, it would give us 4.104. We would note this number, and 0.104, this would again be multiplied by 8. 0.104 multiplied by 8 gives us 0.832. So 0 is noted over here. 0.832 multiplied by 8 gives us 6.656. 6 noted over here, and 0.656 multiplied by 8, right? So it gives us 5.248, right? The number of digits, they are actually specified. We are going to convert it to 3 decimal places, right? So 0.4065, this would be rounded off to 0.407, right? So the process remains the same, only the numbers change. Right, so once we are asked to do the reverse conversion, that is the octal to decimal, so what we can do is it would also follow the same process, right? We would multiply each octal digit by appropriate power of 8, and then we would add the results, right? So 371.4, this would be like 3 into 8 raised power 2 plus 7 into 8 raised power 1 plus 1 into 8 raised power 0 plus 4 into 8 raised power minus 1, right? Once you do this computation, right? So this would actually come out to be 249.5. You can also use a calculator for performing the conversions. Please check out your calculator, right? There are number systems. You can convert to number systems, and you can convert these numbers directly. You can also use the calculator that is available on Windows, right? So there is an option in which you can convert the numbers from between different number systems, right? But calculators, they are used once you are just doing the conversions, right? If you are asked to convert it using the process, so then you would be required to do the complete steps. Right, so if you are asked to convert from decimal to hexadecimal, the process remains the same, only the base changes, right? So you are going to divide by 16, right? So this is how the integer part would be converted, right? If there was a fractional part, right? So you would be again multiplying it by 16, right? So in doing the reverse process conversion, that is, if you are given an hexadecimal, this 0x means that is an hexadecimal, right? So either it would be written something like 2ac base 16, right? Or it would be 0 cross 2ac, right? So this 0 cross means it is in hexadecimal notation, right? So 0 cross 2ac to decimal n, which is n base 10, right? So what we are going to do is the first number is 2, the second one is a, and this is c. So this would be 2 into 16 plus a into 16 plus c into 16. So this would be 16 raised power 0, this would be 16 raised power 1, this would be 16 raised power 2. A is 10, C is actually C is 12, right? So these number are substituted once you do the multiplication, right? And you sum those numbers together, right? So you would obtain this number. Right, so that was we we were doing conversion between decimal and the other number system, right? We can also be asked to convert numbers from binary to octal, or from hexadecimal to octal, or from binary to hexadecimal, right? So there are two methods for performing this conversion. The first method is like if we are asked to convert from binary to octal. So we can convert from binary to decimal, and then we can convert from decimal to octal, right? The second method is that we can convert the numbers directly from binary to octal without going into the decimal, right? So the first process, it is clear to everybody, right? We would go through the step second process, right? So we already talked about this, right? That uh, once that each octal number, it is basically equivalent to 3 bits in binary, right? So what we, once you are asked to convert directly from binary to octal, so what you can do is you need to divide those uh, the stream of the ones and zero into groups of 3 bits, right? And you are going to start from the right side, right, from the least significant. So this would be my first group, right? Then this would be my second group, right? This is going to be my third group, right? And finally this is going to be my fourth group, right? So since this is not, so I can always place a 0 to the left of this, right? So now this 0 1 1, right, it is basically 0 1 1, it is equivalent to 3, right? So I would say this is my 3, right? So this is how the conversion is performed, right? And this 0 1 1, it is equivalent to 3, 1 0 0 is equivalent to 4, this 0 0 1 equivalent to 1, and 0 0 1, right, this is the 0 that I substituted to the left in order to make it a group of 3. So this is equivalent. So this binary number 0 1 0 0 1 1 0 0 0 1 1 in binary, it is equivalent to 1 1 4 3 in octal, right? So similarly, if we are asked to convert vice versa, right? So if it is an octal number and we are asked to convert, so the rule is the same, right? So we can write each octal number as a sum as in the form of 3 binary bits, right? So 5 is basically, if the number is 5 to 7, so we 5 can be written as 101. Similarly, the 2, it can be written as 010, and 7, it can be written as 111, right? So if you remember this table, this is okay. If you do not remember, right, so there are two ways to deal with this, right? Either you start with the table like this is 000, then 001, then we have 010, 011, 100, 101, 110, and 111. This is one way. The second way is that you note down that number, like let's say I've got a 7 over here and I convert it, right? So 2 3s are 6, right? It would give me a 1. Then 2 ones are 2 and it would give me a 1, right? So this is basically equivalent to 7 is equivalent to 111, right? You can use a calculator for the conversion if you want, right? And this is how these numbers are actually converted, right? Similarly, if the binary to hexadecimal is, so this was the first method that we have already studied, and the second method that in the previously we have studied, that a hexadecimal is basically equivalent to 4 binary digits, right? So the same rule is going to be applied, right? So if this is the string, so we would group now them into groups of 4 bits, right? Since each is equivalent to this, right? So I would place a 0 over here, right? So each of these numbers, they can be represented like 1011, right? So 1011 is basically B, 0111 it is 7, 0011 it is 3, and 0101 is 5, right? So you would remember these numbers at the end of the course, right? Once you start dealing with them and keep on doing examples related to them, right? So ultimately you would remember that triple one means 7, 4 ones means uh, 15, 101 means 5, right? So 100 means 4, right? 011 means a 3, right? So this would come once you do some practice, right? So this is how the binary to hexadecimal conversion is performed directly, right? Similarly, if we are asked to convert from hexadecimal to binary, right, and this is some number which is given, so we can write it like this: 0 cross 2 AC, right? So this is 2, this is A and C, and each number it can be written like in terms of 4 bits, right? So this is how the conversion is actually carried out, right? So 2 is 0010, A is basically 10, so 10 once converted to binary it is 1010, and C is 1100, right? So this is how the hexadecimal to binary conversion is carried out using the second method, right? Okay, so now we would talk about different arithmetic operations, right? So arithmetic operations with number and base R follow the same rules as for the decimal numbers. So what are arithmetic operations? The different operations of addition, subtraction, multiplication, division, they are called arithmetic operations, right? So we are familiar with the decimal number system. We would like to learn how to perform these operations in other number systems, right? Other number system, we mean the binary, the hexadecimal and the octal, right? So just remember these rules that whenever you are dealing with base R, right? So you can use only R allowable digits, right? So if you are dealing with base 8, so there cannot be any number greater than 7, right? And all computations are to be performed with R allowable digits, right? So if you do some multiplication like 7 cross 3, it gives you 24, right? So now this 24 needs to be converted into base 8, right? So this would makes sense once we move to the performing some arithmetic operations, right? So we would be performing these arithmetic operation: addition, subtraction and multiplication, right? So once you are doing binary addition, right, the rules are very simple. 0 plus 0 gives you a 0, 0 plus 1 gives you a 1, 1 plus 0 gives you a 1, and 1 plus 1 it gives you a 2, right? But since there isn't any 2, right, in binary number system, so we write the equivalent number, that is 1 0. So this is how the addition is performed. That was the previous slide was about single bits. If you are doing to perform the additions on multiple bits, right? So we have got the augend and the addend, right? And the sum or the result, it would be equal to the sum of those. Like let's say if we have got this, so 0 plus 1 1, 0 plus 0 0, 1 plus 0 1, 1 plus 0 1, and 0 plus 1 1, right? And these are the carries, right? The default carry is going to be in the least significant bit, it is going to be by default, it is going to be a 0, right? Similarly, we have got these two numbers. 0 plus 1 gives us a 1, 1 plus 1 it gives us a 2, which is equal to 1 0. So 0 would be written over here, the 1 would become a carry. 1 plus 1 plus 1, it would gives us a 3, which is equivalent to 1 1. So 1 would be written over here, the 1 would become a carry. 1 plus 0 becomes a 1. 1 plus 1 plus 0 becomes a 2. 0 written over here, 1 becomes a carry, and that would come here, right? So this is how binary addition is performed, right? In the same way, you can perform binary subtractions, right? So if you are going to, this number is called subtrahend, and the number from which you are subtracting, that is called minuend, right? So if you are subtracting this number from this, if this number is greater, right, so then it's okay, there is no problem, right? But if it is the number from which you are subtracting, if that is smaller than the number which you are subtracting, right, let's say this is A, right, and this is B, right? If you are doing A minus B, right, and A is greater, then this is okay, right? But if you are doing A minus B and B is greater and A is smaller, right? So which means B is greater than A, right? So you cannot carry out this subtraction like this. So what we normally do is, in decimal number system, let's say if we are subtracting something like 5 minus 9, right? So we do not do 5 minus 9. Instead, what we do is we perform 9 minus 5, right? The sum is 4, right? And then we place a minus sign, right? So 9 minus 5 would be equal to minus 4, right? So this is the same process that we are going to use over here. If the number which is going to be subtracted, the B is greater than A, so we interchange the numbers, that is what we did over here, right, and carry out the subtraction, and then we append a negative sign to the result, right? So this is exactly the same process, right, that is explained over here, right? Similarly, if we talk about the binary multiplications, so these are the single bit rules like 0 multiplied by 0, 0, 1 multiplied by 0, 0, 0 multiplied by 1, 0, and 1 multiplied by 1 is a 1, right? So this is how the binary multiplication is performed. This is self-explanatory. You can go through this on your own, right? Okay, then we have got some a little bit of complicated operations, which is the hexadecimal addition, right? So if we are doing this by hand, so it would be easiest to convert each set of digits to decimal and back. That is one way, right? Or we can do it directly, right? So we are asked to add these two numbers 59F and E46, right? So F is basically 15, right? So 15 plus 6. What is 15 plus 6? 15 plus 6 gives us 15 plus 5, 20 and 21, right? So 15 plus 6 gives us 21, right? But this 21 is a decimal number, right? It needs to be converted into uh, the uh, the hexadecimal, right? So it would be written as a sum of 16 plus something, right? So it would be 16 would mean a power of 1, right? And this 5 is the number which would actually be written over here, right? Then the next digit we have 9 plus 4 along with a carry of 1, right? So this 16 would actually translate to a carry of 1, right? So 9 plus 1, it is 10, 10 plus 4, 14. What is 14? That is E, so it would written as E. Then 5 plus E, E is 14, so 14 plus 5, 14, 15, 16, 17, 18, 19. But we cannot have a number as 19, right? So we are going to express 19 as a sum of 5 plus 4, 14 gives us 19, so 19 would be expressed as 16 plus 3, right? So it would gives us the 1 would become a carry and 3. So this 3 would be written over here, right? The 1 would become a carry, which is actually written over here, right? So let's say you have got a number which is greater than 16, right? So what you are going to do is you are going to divide that number by 16 and you are going to write the remainder over here, and the number of powers of 16 that would be written over here as the carries, right? So over here fortunately we have got 1 times 16, right? But there can be a number which can be multiple times of 16, right? So in that case, the carry might become a 2, right? So if this was, let's say, instead of 21, it was 21 plus 16 more, right? So then it would be 16 cross 2 plus 5, right? So the carry would become a 2 then, right? Because we are carrying. This is how actually things happen in decimal, right? But since we are very much familiar with dealing with them and decimal, so the process is quite easy, right? Please do some examples on your own. This would then be self-explanatory, right? So similarly, if we are asked to perform octal multiplication of two numbers, that is 762 and 45, right? So we would write them like this: 762 multiplied by 45, right? So 5 twos are 10, right? So then this 10 would actually be expressed as 5 multiplied by 2 is equal to 10. So 10 is equal to, we would denote that in terms of 8, right? So 8 plus 2, right? So this 2 would be written over here. This 8 would move to this place, right? In terms of this would be 1 times 8. So this is a carry of 1, right? Similarly, 5 6 are 30 plus 1, 31, right? 5 6 are 30 plus 1, 31. So now we are going to express 30 in 31 in terms of parts of 8 and along with some remainder, right? So the easiest way for this would be like if you divide it by 8, right? So 8 threes are 24, right? And you get a 7, right? So it is equal to 24 plus 7, right? The 7 would be written over here, that is the remainder, right? and this 24 is 3 times 8, right? So the 3 would become a carry. Now we are going to multiply 7 by 5. So 5 sevens are 35, right? Plus 3, 38, right? So 5 sevens are 35 plus 3, 38, right? 38 is equal to 8 cross 4, that is 32, plus 6, right? So 6 would be written over here, right? 4 would become a carry that would be written in this steps. So this is how this is going to be performed, right? Similarly, you can perform the rest on your own, right? 762 multiplied by 4. Once you do the multiplication, you are going to express it in terms of powers of 8, right? And right there. So once this all multiplication is done, you obtain this 3710. Then you are going to carry out the addition of these. Like this would be 2, 7 plus 0, 7, 6 plus 1, 7, 4 plus 7, right? This becomes 11, right? But then 11 needs to be expressed in terms of like 4 plus 7, it is equal to 11. 11 is equal to 8 plus 3, right? So this 3 would come here, right? And this 8 would be in terms of power of 1, it would actually come here, right? So this would be 3 plus 1 equal to 4, right? So this is how these are the some of the important operations that we need to perform, right? So you should always be remembering the rules once you are doing these arithmetic operations and different number systems. So if you have any question, you can post in the question and answer thread on the Piazza group. The details would be shared in the next slide. Next time we would study about the various alphanumeric codes, the decimal codes and the gray codes, and with that lecture we would come to the end of chapter 1.